In this video, I would like to provide the basic definition for regular ocean waves. While the potential of ocean waves has long attached humanity, it is only in recent decades that practically feasible energy extraction schemes have emerged. The shift from historical curiosity to modern engineering reflects our deepening understanding of fluid mechanics and also developments in structural resilience and design in the ocean. The wave energy can be catastrophic when it becomes extreme, as seen in 2011 Fukushima accident where a massive tsunami overwhelmed coastal defenses, where demonstrating that the sea's power is as destructive as it is productive. Ocean waves are primarily categorized by their restoring force and their period. By restoring force, I mean physical mechanism that pushes the water back toward equilibrium. The wave period, as shown in this figure, ranges from fractions of a second to several hours. At the smallest scale, capillary waves, ripples are governed by surface tension and generated by light breezes. As wind energy increases, the restoring force shifts to gravity, forming gravity waves. On much vaster scales, tsunami and storm surges are long period waves triggered by seismic events or extreme atmospheric pressure shifts. Finally, tides represent the largest wave type with periods of 12 or 24 hours, driven by the gravitational pull of the moon and sun. In this video, I focus on the gravity waves with period ranging between 1 to 30 seconds. That the generating force is wind and restoring force is gravity. Now, let's talk about the generation mechanism. There are different wave formation theories like Miles theory and Jeffreys theory, that here I focus only on Jeffreys wave propagation theory that is based on pressure gradients. Assume wind is blowing over wave crest as shown in here. In the upwind side, the wind hits the back of the wave directly, creating a region of high pressure shown by HP or this plus sign. Alternatively, in the downwind direction, here we have sheltered zone for the wind and the flow detached from the surface, creating a localized eddy as shown here. This results in region of low pressure here. We have high pressure pushing down on the rising side of the wave, the back, and low pressure, you see the eddy, pulling up on the falling side of the front of the wave. The wind in this case is doing a positive work that is converted into the wave's potential and kinetic energy, causing the wave amplitude to increase over time. Now let's move on without more details on generation mechanism. Ocean gravity waves generated by wind can be categorized in at least in two distinct states. Wind sea generated by local wind and swell non-local generated by remote wind. Wind sea are waves generated by local wind currently blowing over the surface. They are young, waves that are irregular and complex in their shape. Non-local waves are called swell waves. These waves are generated by other wind in far distances, as shown in this figure, that the generated wind here is propagated over a certain distances, which is called fetch, and here we have these swell waves. Regular waves are idealized waves like sine or cosine waves that maintain a constant height, constant period, and constant direction. The highest point in a regular wave is called crest, and the lowest point is called trough. Let's define few key parameters in linear or irregular wave theory. Wave height is the vertical distance from the crest to the trough. The wave amplitude is half of a wave height. Wave period is the time it takes for two successive crests or trough to pass a fixed point. If we have a water particle located on the crest, the time it takes this particle travels to the next crest. Wavelength lambda is the horizontal distance between two successive crests or trough. Wave frequency is the number of complete wave cycles that pass a fixed point in 1 second. Its unit is hertz, or 1 divided by a period. Wave stiffness is a dimensionless ratio that describes how sharp a wave is. It is the ratio of the wave height h to the wave number lambda. For example, in deep water, a wave begins to break when the stiffness exceeds approximately 1/7 as one of the criteria for the wave breaking. The wave number represents the spatial frequency of the wave and is defined as K, and its unit is radian per meter. The surface elevation, zeta, is the vertical position of each point with respect to the zero level, and is given by this formula. Zeta is equal a cosine omega t minus kx. And omega is angular frequency, 2 pi divided by period. Its unit is radian per second. Now we have angular frequency in time and wave number frequency in space. Dispersion relation is going to bridge between time and space. Omega represent here time and K represent wave number in a space. It simply says that in a specific water depth, a wave with a given spatial shape K can oscillate at a single angular frequency omega. Remember, definition of wave number 2 pi divided by lambda. A long wave with large value of lambda has a small wave number that must oscillate with small angular frequency. On the other hand, the short wave with large value of wave number must oscillate quickly. While there are different definitions for deep and shallow water, assume we define deep water. When water depth is greater than half a wave number, in this case, tangent hyperbolic KH in dispersion relation approaches to 1, and dispersion relation is simplified as omega squared approximately equal to GK. For shallow water, when water depth is less than wavelength divided by 20, tangent hyperbolic KH for small kh approaches to KH, and this modifies the dispersion relation. Now we have learned the basic characteristics of regular waves like wave height, wave amplitude, wave length, wave period, wave frequency, wave steepness, wave number, and wave angular frequency. There are other important characteristics that I'm going to discuss in this slide. Regular wave phase speed and energy density per surface area or wave energy. Phase speed is simply the speed at which an individual wave crest moves across the water surface. Assume we are watching one point at the crest of this wave. Here the speed of this point anytime is called phase speed. It is defined simply as distance divided by time. Distance lambda, wave length, time, wave period. Using dispersion relation, which connect between time and space, this phase speed can be represented by omega divided by k. For linear gravity wave, which we have a sine or cosine wave, the average energy density per unit surface area, also called wave energy, is given by this formula. The wave energy contains both kinetic energy and potential energy of regular waves, and its unit is joule per meter squared. According to the formula, notice that the energy is proportional to the square of amplitude. If we have high doubles, the energy density increases by a factor of 4. In the next video, I discuss about linear wave theory.